this is Kim Nelson, Professor Nelson with the Jewelry Design Department at FIT, doing another tutorial for us class. This tutorial is really more of a design tutorial. It's not a Rhino or modeling tutorial, and it's about the principles of hand drawing a 3/4 view for a ring. Ironically, I'll be demonstrating it in Rhino because it's just a lot faster and easier to communicate in. The main principle you want to be aware of is that when you draw a 3/4 view, the idea is that your 3/4 view is revolving around a sphere, and that sphere equals some known dimension in your drawing. In our case, it's almost always 17 millimeters, which is a ring bore. Okay, so you draw your circle with the template you have that is closest to 17 millimeters, and then you have an ellipse template of the same size. Ellipse templates are laid out on the template in terms of degree and length. The number you see as far as this measurement is its length. So you find a ellipse that is as close to that 17 millimeters circle that you used. For example, if I am not mistaken, 17 millimeters is an 11/16 inch in inches, an 11/16 circle, so you would use an 11/16 oval. The other dimension on ovals is a degree dimension. On templates I laid out in increments of 10 degrees, 10, 20, 30, 40, 50, 60. The higher the number, the fatter the ellipse. Okay? So you'll pick an ellipse that represents what you most want to see in your ring, and this is the first main tip, and that is that the width of the ellipse determines how much of the front view of your ring you're going to see. When you are laying out a design, you really want to be thinking about what do you want to see most. 3/4 view, a true 3/4 view, allows you to see 3 views of your ring at once, top, front, and side, but it doesn't let you see them equally. So you have to pick what is most important. So if the front view is important, you will have a wider ellipse. If the front view is less important, you'll have a narrower one. Okay? So I have my ellipse. The next important thing to remember is that you're drawing in 3/4 view. You're drawing in perspective. So this sphere, the reason I chose a sphere is because a sphere is a sphere is a sphere, independent of any view you might be looking at it from. So you can draw a circle around that sphere, and that will always appear as an ellipse in 3/4 view. The first axis, because when you design or draw a 3/4 view, you do have to be aware of axes, just like you would in a 3D modeling program. And the easiest axis to kind of get your head around is the one that runs perpendicular to your ellipse. It basically runs through the short pole of your ellipse. Okay, so just going to extend this curve there. So that would be our y-axis, and you can picture how this is interacting in your drawing as it being a tube. Okay, so you can see that it basically looks like a section of tube. And you wouldn't start your drawing this way. This is what you want to have in mind. You want to be aware that when you draw this ellipse, you are essentially representing a segment of tube. It centers itself up around the middle of a sphere. Okay? Like so. Okay, so keep that in mind. And that tube is created by simply offsetting the y-axis, which is in green, just like it would be in Rhino. Okay, so this is the first principle. The width of your ellipse determines how much of the front view you're going to see, and that your main axis along which this ellipse travels is the y-axis, and it's simply done by connecting the two quadrants, the short pole of this ellipse. Okay, Now, to have a true 3/4 view, that ellipse can't be straight up and down. Straight up and down is really kind of a perspective side view, and it won't allow you to see much of the third view. If you leave this as it is, it's not a true 3/4 view, because you can see part of the side and part of the front, but you can't see any of the top. Okay? To make it a true 3/4 view, we have to rotate that sphere. So in your drawing, you would simply just rotate the ellipse around the center of your circle. And the easiest way to do that is to simply line the edges of your ellipse up with the edges of a circle, your circle template. So you start this process by drawing that circle, picking an ellipse, selecting it based on its width, and laying it down over the circle template to get the width or the amount of top view you want to see. If you go to straight horizontal, you're no longer in a true 3/4 view again. Now all you can see is the top and the front, and none of the side. So you want something in between. Okay? Anywhere in here is fine. Just beware, do you want more top? Do you want more side? I'm going to give us more side for this drawing. Okay. And there is that axis that we had. That y-axis has followed along, of course. It's because I'm in Rhino in your case. After placing this, you would line up a ruler through the ticks on your ellipse, and which are present on your ellipse template. So you would mark when you drew your ellipse template from your ellipse template, and then connect the dots. Okay. I'm going to quit now referring over much to hand drawing tools, because it's just going to make this wordy and hard to follow. But understand that I would do all of this with using simply a circle template, an ellipse template, and a see-through graph ruler on top of a grid pad. That's all I would use to make this. Okay. Next principle is that the z-axis in this method is always straight up and down. Like so. That does not change. It does not matter what angle you rotate this to. This axis never moves. If it comes straight up and down, then you lose the side view, because the y-axis and the x-axis become the same. Okay. That line doesn't move. Alright, so now that we have that concept, the next important concept to have is that any circular shape that runs along this axis, and in the case of a ring that's going to be a stone, okay, is going to be simply a horizontal ellipse. That's because we're going to do a 6.5 millimeter stone, standard 1 carat. That's because any ellipse drawn on this is simply creating a pipe out of this as well. Okay. Like so. And since that's the case, any girdle of a round stone is going to simply be depicted as a horizontal ellipse. Okay. Now, I made the thickness of that ellipse by eye. If I'd have made it too narrow, it wouldn't seem round. If I made it too wide, it wouldn't seem round. Now I will show you how to get that absolutely precise, but for the purposes of what we're doing, it's only important. How frustrating. It does end up being almost in the exact same place. Alright. It's just to remember that you are dealing with a visual eye-by measurement most of the time. I rarely do the full mathematical spread on this. I do exactly what I'm doing here. I draw an ellipse for the ring shank, and then I draw another horizontal ellipse for my stone. Okay, but you can see if I make this too round, that doesn't look like a round stone anymore. It just looks crazy. And if I make it too narrow, that doesn't look like a round stone either. So I would use my circle template, my ellipse template, lay it down dead horizontal, and try different fatnesses of ellipses, higher degrees of ellipses, lower degrees of ellipses, until I get an ellipse that visually to me makes it look like a round stone. And that's fine. Okay? The third thing, okay? So first thing was choosing the proper ellipse and rotating it, depending on what you want to see, how much of the front, top, or side you want to see. The second principle is you have a vertical z-axis at all times, and so therefore any stone, any circular shape that's going to run an elevation above that ring is going to simply be a horizontal ellipse, and you would set that horizontal ellipse yourself by eye by trying different templates until you got one that looked round. Okay. Next is the concept that to create other ellipses concentrically around this, you simply pick a longer ellipse and of the same degree and line it up. Okay, an example of that shown flat on. Say I have a circle and it's 17 millimeters in diameter, and I want to offset that circle 2 millimeters to create the thickness of my ring shank. That's concentric, one inside the other. You can imagine when this is turned in perspective, neither one of these are circles anymore. They will both be ellipses, and this distance will not stay the same all the way around, because any distance along the z-axis is foreshortened. Okay? So it's a simple concept, because this represents, remember, this represents a 17 millimeter circle. It's a 17 millimeter sphere. Alright? It's drawn in the middle and rotated so it doesn't look like the full 17 millimeter sphere anymore, but it is. Its length kisses that 17 millimeter sphere on both sides. If it cuts that 17 millimeter sphere, you end up with something that looks like a sliced grapefruit. And that means that the true height and depth of this z-axis, the 17 millimeter height, is right there, because that's the top of the sphere, that's the bottom of the sphere, and this is the line going around because the sphere has rotated towards you. Okay, so it's foreshortened. All right, since it's foreshortened, the distances at the top are going to get narrower. The ones on this side will remain the same. So, keeping that in mind, all I need to do is grab another template, another ellipse off my template that is the same degree as this. Say this is roughly a 40-degree template. Grab a 40-degree template, but grab it larger. Okay? In this case, we want to make it 21 millimeters, which I believe is 13/16 or something like that on a circle template. Okay? So, I'm just going to grab a larger template. I'm going to do that by scaling the one I have. And So that's the same ellipse. You can actually test it by, I did it on a computer, so you know it's right. But if I offset this by 2 millimeters, you'll see that it intersects it. Okay. In effect, giving me that. That's the thickness of our ring shank. Remember, this looks like now a bowl sliced. The front face of this actually represents 2 concentric circles, but now in perspective. And the top distance along the z-axis and the bottom along the z-axis are thinner and compressed because they're foreshortened. Okay? So, once again, basic concept that we can create as many concentric ellipses around the middle one that we want to by simply using a longer ellipse, a bigger ellipse, centered up on our smaller ellipse, as long as it maintains the same degree, the same shape of ellipse, the same 30 degree, 40 degree, 50 degree. And you would line that up in your drawing very easily by lining it up along this y-axis, because that y-axis is going to stay the same for both of these. Okay. Okay. So what was the same thing that works on a pipe for the inside works to draw a pipe from the outside. Okay. I'll keep those for later. So that's really it, guys. That's really the main concepts of setting this up. Now, if I want to go into more detail, which I do, and I'm going to have to get a little more sophisticated than that. Okay? I want to make my shank 2 millimeters thick. These 2 lines indicate the center line of my shank. Center inside shank, center outside shank. To draw the rest of my shank, I simply need to slide this, the appropriate distance, my template, back and forth to draw the 2 sides of my ring. Okay? In principle, something as easy as that. If I slide that template, the exact same template I used to draw this, a little ways that way and a little ways this way, I've drawn the thickness of my shank. Okay? Just fine if I don't want to be precise. If I want to be precise, I'm going to tick off the measurements for that thickness right here. Okay? So I want it 2 millimeters thick, so I'm going to tick off a millimeter on each side. The easiest way to draw that in Rhino is just to use a circle. And I'll just lay it out here. And I'll make it a 2 millimeter diameter. That'll give me a millimeter on either side. And I'll do the same thing up here, so that both of these have the offset distance measured. And then I take my template and slide it along the y-axis until it intersects with both of those marks. That's my inside shank, which I will make a different color. And now the same for the bigger ellipse for my outside shank. And with that, I have drawn the inside and outside of my shank at a very accurate 2 millimeters. Okay. To finish up my drawing, I just draw a line parallel to my y-axis, connecting the edges of those pipes, that cylinder. Use my ruler, lay it down, have a graph ruler so I can line it up even with that. And I've got it. Now if I want to erase anything that would not be visible in an opaque shank, this one is currently glass, I just come in with my eraser shield and I erase it. And I have drawn my shank. Okay, a 3/4 view depiction of that. Okay. So bringing back my x-axis, my z-axis information and my original construction lines, because we're going to do some more in-depth drawing. I am going to obviously click the wrong curve. Just lengthening my z-axis so I can have further use of it. I'm going to draw this same 2 circles into the right view over here. This will become the right view, the right orthographic view that corresponds, the side orthographic view that corresponds to my 3/4 view. So I would use the same 2 templates, 17, 21 millimeter, 11 16ths, 13 16ths inch, whatever you have or working with. And I'll bring it over to the side. Okay. Now I want to bring the same information over. I want to draw the center line of my shank. Across this at the right angle. Remember, it's tilting towards me, and I know it's tilting towards me because I can see part of the top view of the ring, right? It's right there. Okay? So since I know it's tilting towards me, I know that this line, this center line, will be somewhat of an angle over here. Okay, so what angle is what I want to discover right now, and it's not terribly hard to figure out. I'm going to bring a construction line straight over from where this top center line intersects the z-axis until it hits my larger circle in the side orthographic view. And I need to do the same thing down here. The challenge is going to be that I erased that when I cleaned up my drawing. So to do this properly, do not clean up your drawing until you're ready to. Actually, there we go. So I'll bring that back to where we were. And paste, yeah, there we go. There's our original with all the lines. So, as I said, take a construction line over from where the center line of the top, outermost shank, intersects the z-axis, and where the bottom of the outermost shank reaches the far side. Okay? once I have that, I know where that line is. It's right here. Okay? Now, if you're in a hurry, you could also simply have drawn it from the topmost. And then if you drew a circle, sorry, not a circle, if you drew a line connecting the center of your circle to that construction line, the bottom line, if you drew a line all the way across your circle, you'd get the same distance, the exact same curve. Okay? Can extend this line, because not only does this line represent this center outer line, it also represents the z-axis. This z-axis is actually laying this main outer circle, ellipse in this case because it's in perspective, is laying right along this z-axis. So we're going to make this as our z-axis as well. Like so. This gives us quite a bit more power than we had before as far as getting accurate information. Now, if I wanted to, by the way, I could certainly draw the side view of my shank over here. It's 1 millimeter on both sides. It's a 2 millimeter total thickness, and it's got a connecting line right here. Except for I can't. It won't let me grab it. Fine, I'll just do it by eye. Rhino has a hard time pulling perpendicular lines accurately at an intersection when there's more than one curve involved. That's close enough. So, I've effectively now drawn the side view of my shank. I didn't do this in class, but I did discuss why I'm doing it in class. Here's my side view. Okay? The only line you can take any measurements off for drawing this accurate three-quarter view is the center line. The axes. Okay? Those are the only lines that have any correlation. This axis relates to this axis. This line that's on the center line relates to this line. You can't take any information at all off of any line that is not on an axis. You can't ignore them. It's nice to have them there, but you can't take dimensions off of them. Okay? That's just important to keep in mind. Now, if I wish to draw this y-axis over here in the side, that's simple enough to do. It's simply perpendicular to the z-axis. Okay. Now, these aren't perpendicular to each other because you're in perspective. But in orthographic view, they are. Okay? This is in perspective. This is straight from the side. Okay, so I am going to now bring in the stone. I had drawn it ahead of time. From the top and side. I'm going to take the side view of that stone, and I'm going to place it over here. Now, if I'm doing this with a graph pad, I would actually could have it drawn on tracing paper and slide it underneath. which is exactly what I did for years. And then rotate it into position here in Rhino. And now I have a side view of my 6.5mm stone lined up along my rotated z-axis in my orthographic side view, which I can now carry information over into my side view. I'm thinking and talking at the same time, not wise, into my 3/4 view. So, first information I want to have is, where is my girdle going to lie? That's simple enough. I bring over a construction line from where my girdle intersects the rotated z-axis, and bring it straight over until it connects with my regular z-axis. And this will be the elevation for my stone. Okay. I had drawn the 6.5mm wide in the beginning to show that I could hand sketch in that girdle line. I know that's an accurate dimension because, remember, all circles in perspective in this method are horizontal, and if they're horizontal ellipses, then the width is just a side-to-side offset or a straight horizontal measurement. So these do correlate to the actual width of the stone. Okay? So I have that. Okay? So, I know that's where the girdle would actually be. I can also find out how deep my girdle is, okay? But you will notice that now that elevation is not found on my z-axis. I can't, there's no way I can bring this information back and forth, okay? So I need to now create a line that is exactly parallel to my y-axis in my perspective view. So I'm going to bring a copy of this up. In a hand drawn, I would just use my grid ruler to do it, and put it right here in my intersection of where my girdle is running to and fro, like so. And now I can bring a construction line from the front edge of that circle in the side view to where it intersects. Actually, no, take that back. Got ahead of myself. That's for later. Actually, I just bring this straight over to the z-axis. I almost forgot what I told you, to make sure I can't take any measurements off anything that is not an axis line. Bring this over, there. And now I can draw the ellipse for my girdle. It will be the width of 6.5mm, and it will be the depth or degree that is equal to this width in the right view or side view carried over to the z-axis. And I'll delete those construction lines as well as these, because it's going to get a little bit busy to have them all there. Also going to hide these for a bit so we don't need them. Alright, I'm going to bring back my one I drew by hand earlier to see how right or wrong I was. I had drawn it too low, okay? Where I drew it, the culet would be down into here. And as far as the width goes by eye, my eye was pretty good. I drew it a little too fat, but not much. So, like I said, in the practical application of these principles, I would usually just draw it by eye and by hand, using as much of this information as I find helpful to use in a hurry. But if I want it accurate, I can get it accurate. I'm going to take it a further level of accuracy. I'm going to draw in my table and my, okay, actually I didn't need to draw that construction line. We know that the culet falls right where the z-axis meets the top of our shank. So I will put a reference point there, just so we can see that that's where our culet would be. And I'm going to use the same steps to draw the table that I used to draw the girdle. I need the elevation. That's the elevation of my table. Okay. I need its elevation also at the front edge and back edge. And I need to bring up its width. And with this information, I can draw an ellipse that is close. Now, on a computer, I can get the exact ellipse. You guys are using circle templates. It's going to be whatever degree template comes closest to this. But that allows me to draw the table of my stone in perspective. And you'll see that looks very believable. Okay. This will suffice for your homework, but I do want to show you how to use this information to draw something more sophisticated. And to do that, we're going to need to have our x-axis. Okay? Now, our x-axis is the axis going this way. Okay? To find that x-axis, the way I do it, once again I'll do it by eye, and I'll do it by math, so you can see the way I would approach it each way. To do it by eye, first thing I need to do is to draw a line perpendicular, or parallel I should say, to my z-axis. The full width of my center line. Remember, everything's about center lines. So there we have it. Now, I've erased this. If you've erased this in your drawing, it will be hard for you. So once again, don't clean your drawings up until you're completely finished. I'm cleaning mine up as I go so that you can follow me more easily. And because I have Rhino, so I can just offset both sides. If I offset this side, it'll be accurate over here. Drawing by hand, you do not have that safety. Okay, to create my x-axis by eye, I'll just put my ruler right here at where my z-axis is running into the top of my ring. Then I'll tilt it like a teeter-totter until these two triangles are roughly the same. Right now this one's a little smaller. But also making sure that up in here, now by eye with a pencil it's much harder to do, that things seem even and equal right at that line as well. Okay? So these two triangles are reasonably visually the same. That would be my x-axis. However, if I want it to be really, really accurate, then I would have to draw a line using my ruler from the intersection at the middle of my z and y axis. Basically my world 0, 0 in this case, to where this line first touches my center line. Now I've done all this by eye. This isn't exactly accurate. This should actually come out a little bit. Which means that would as well. Which means that that point would be in a little different place. But it's the same idea. And it would be reasonably accurate either way. Now you can see here's the one I drew mathematically correct. Here's the one I drew by eye. The one I drew by eye is a little going up too high here, and I could actually kind of see that because this triangle is still a little larger than this one. Okay, that's my x-axis. With my x-axis in place, I can use a grid ruler to draw a parallel line at any location I would like. Okay? And with that ability, I can also do the same with the y-axis. And I can replicate this relationship anywhere up and down along the z-axis I want. And that's going to be very important to do more sophisticated drawings. Bringing back my stone. Okay. I would like to be able to draw a center line crossing this stone in both directions. To do that, all I need is to establish the center line where it falls here. Now I could have done that by bringing it from here over, or by just drawing across the axis. Either way would give me that information. All I need is this intersection point. Okay. If I have that intersection point, I can bring this relationship to that position. To any position along the z-axis that I want it to. And once I have that, I can draw that center line, the x-axis at the girdle, x-axis at the table, table, girdle, y-axis at the girdle, table, table, girdle. with that done, you can see that I have a nice accurate center line drawn. For my stone. Okay. So this can be extremely helpful for putting these details anywhere that you want them. Okay. We're done. I do want to show you why that's important, however. What if my stone wasn't a 6.5 by 6.5 circle? What if it was a 6.5 by 4 pear shape? Like this. Let's make it a 4.5. Just going to draw this zone quickly. So there's our pear shape. I'm going to keep this. It will prove important in a minute. I'm going to draw the side view of my stone. In this case, the stone, we take our heights for our stone, we take them off of the narrower dimension for the stone. I am not, well, I'll do that. So narrower dimension was 4.5. You'll notice that I'm typing equations in here. If you hit equal and then do an equation in the bracket, Rhino will do the math for you. So I'm typing in 4.5 times 0.431. That's, and then the other parenthesis, and that will, Rhino will do the math to give me that exact distance, which I hold Shift key, and I've got it done. As quick as that. I have the side view for my pear shape. Notice that this pear shape fits inside of a circle. Any stone can fit inside of a circle. So, with that pear shape, falling inside of that circle, I can plot it inside of this circle with this information that I have. So, for example, I'm going to now move the side view for this stone up. Line it up along the side view z-axis. Okay. In the interest of time, I'm actually going to move it up until it's in the same position as the center line of this girdle. So that puts the center of the girdle for this stone quite a ways up. So my stone's floating in space a little bit, but that's okay. I am going to bring my X and Y lines up using my parallel ruler. This circle in perspective equals this circle in perspective. Okay? And that's very helpful to being able to draw this stone in place. Okay? For our purposes, there is one more step we can take this to. I don't think I will go there just as yet because that's a long ways to go. I am going to borrow this so that I can well, I really don't need to leave it where it is. I can bring the table up, but the first thing I would do is draw the shape of that stone. Now I would do it by hand, honestly. I wouldn't plot it out, even though I can. I would just do it by hand. I would bring this into position, or be aware of it and see that it basically breaks through here. At about that far. Okay. And start to draw it. Now I know it's a circle at the top. So I know that it's going to follow smoothly across there. If I take it all the way, right, it will make it A. But something like that. drawing with a pencil, would be an accurate girdle for that shape. Okay, so that is the thing to be aware of as you're drawing this. And you can try and extrapolate all you want. I invented this, so I extrapolated all over the place to figure out what I was doing as I was going along. But this half of this stone is a 4.5 millimeter ellipse. Okay, and we know that in perspective drawing, all circles, it's a 4.5 millimeter circle, all circles are a horizontal ellipse. So if I bring this down in some variation, it should be able to be useful to me in some way in drawing this stone down here. The halfway point for that, the quadrant for that 4.5 millimeter circle, is located here. So since we would have that parallel to this, I could visualize how far that distance is. Okay? And, move this into position in some way. Now I may need it thinner, I may need it thicker, I may need to change it, but the principle's sound. I can use that horizontal ellipse as part of the shape for that, okay? But I would just draw it by hand, okay? And that's really enough. The last teaser I will leave you with is I've shown you can do an orthographic side for your perspective. You can also do an orthographic top. In the orthographic top, the most important piece of information for you is going to be the x-axis. Both the x and the y. You can't see the z because the z is coming straight at you. Here you can't see the x because it's coming straight at you. But you can see z and y, just like right now. Here we'll be able to see x and y. Once again, working off the principle of a sphere, working off our center line of our outer shank, carried straight up until it intersects our outer larger circle, because this is the outside of the shank, this is the outside of the shank. That same line on the other side, carried through, connect those two lines through the center, and that is your x-axis. And as always, our y-axis is perpendicular. In the orthographic view. Okay, so with that in mind, I can place any stone information in here, and I can carry that information down. Back and forth between the views. And as long as I stay on center lines, the relationship will hold true. Okay? So that's important information to have. Alright, so I could actually plot exactly where this line is by coming down from that y-axis onto this y-axis and using my ruler to carry that back. And that would actually be an exact relationship. Okay? So that's where the quadrant of an actual ellipse would begin. And it would have to come through here to over here, and then my point would begin from there to there, which would allow me to draw my ellipse more accurately. To be able to have it stay smooth coming off here. Smooth through here, around here, and you get the idea. I'm trying all kinds of clever ways because sketching in Rhino is really not easy to do. I would actually do this in Painter or with a pencil before I would do it in here. But there. There. Yes, there we go. That would allow me to draw a better version of that stone. Okay? So this is true. You can plot information. I used to take my top view of my designs on tracing paper, tape it underneath on a top wheel, top sphere, to take the side view, tape it underneath on the side wheel, side sphere, and then carry information back over. The relationship between this and this creates this. Okay? So even though I start here, in reality, you could also work in reverse. You could actually decide how much of the top view you wanted to see, or how much of the side view you wanted to see, and you could plot your whole design accordingly from there. Okay? So that's just to open up your mind to some of the possibilities that exist with drawing this way. There are a number. Okay, going to clean this up. lost the, there. Nope, don't want to lose that. Okay, so. For example, I want to see a lot of the top view. If I took my side view and rotated it so that the top of the stone is almost facing me. Okay? If I do that, where my center line intersects and my center line intersects, is going to dictate what kind of ellipse I can put here. Because my ellipse has to fit in between those, right? No matter what I do, it has to fit. Okay, so obviously it won't fit right now. You can come to an approximate fit. Doing this. Okay, that would be this looking straight at you without any information up here. But now if I want to see a side view, this is going to get narrower and narrower. If I want to see any of my side, this is going to have to get skinnier. Because it's a relationship between the two. So this has already dictated what my top is going to be. If I want to see a side view, even that much side view, okay, then this ellipse is going to have to be scaled until it fits. Inside of those parameters. Okay, so that's all of the top view, of the front view I could possibly see, and that's just showing a little bit of side view. Okay, if I wanted to see more of the side, then my ellipse would have to scale down even more. Okay? And if I wanted to see what that was actually looking like up here, remember, z-axis never changes. The other two do. I would first have to plot my x-axis. that would be the corresponding x-axis from here. The y-axis is across the short poles. Of the axis of the ellipse in the perspective view, and in the top view it just runs perpendicular. Okay, so now I have my axis lines and I can start drawing again. So you could actually create this from any view and carry it into the 3/4 view by rotating your views. These wheels all work together. Okay, that's it. That's probably more than you wanted. Thanks a lot. I'll see you next week.